Okay, so in this time there's quite a few homeworks, so I think I'll use the record so for you guys you can check in your free times. Okay, so let's start to review the homework. Okay, so for the first question, we need to determine why inside a BCC structure the A equals to this thing. Okay, so in order to solve it, we first need to know the structure of BCC. So there's in the center of the cubic, there's also additional one atom inside. So the close packing direction is here. So we need to use this length to determine why A equals to this. Okay, so first we know that we need to use this triangle. So we know QP equals to A, and then we need to know how long is MP. So we want to solve this, we can use A squared added by A squared equals to MP squared. So we know that MP squared equals to 2A squared. Okay, so then we need to know this. So use the same method. NP squared equals by PQ squared equals to NQ squared. Okay, so we put 2A squared added by 1A squared equals to 3A squared. So we know this length equals to the square root of 3 times A. So we know this length also equals to 4 radius of the atom. Here's 1, and for this there's 2 radius, which is the diameter of this, and then here's 1 additional radius. Okay, so if we know this, this equals to this, so we can organize the equation and we can get A equals to this. Okay, so this is for 3.3. Okay, for 3.4, we need to know the atomic packing factor of HCP. Okay, so what is atomic packing factor? First, we use the total volume of the sphere, which is also the atom, divided by the total volume of the unit cell. Okay, so for HCP, we know the coordination number is 6, which means that inside the unit cell there's 6 atoms, and each atom has the volume of this, because this is the equation for a sphere. Okay, so the radius we need to know, and then afterwards we can know that Vs equals to 8 times pi times r cubic. Okay, and then for the volume of a unit cell, we know that we can use the base times the height equals to the total volume of a HCP cell. So this is the equation, and we also know C equals to 1.633A. Okay, so which we also know A equals to 2R for HCP. Okay, so we can get this equation, and then we put it inside to get the result of VC. And for atomic packing factor, we take this divided by this, and then we can get the answer. If you press the calculator, then you can get 0.74. Okay. And for question 3.6, we need to calculate the radius of TA. Given that TA have a BCC crystal structure and the density is given also, and also the atomic weight. Okay, so for BCC structure, what we need to know is that the volume of the unit cell is a cubic, so equals to A cubic. Okay, and A also equals to this because it is a BCC structure, and the coordination and the atom inside this unit cell is 2. We have 2 atoms inside. Okay, so first we want to use R to symbolize both. We want to use R to symbolize the volume of the cubic. So we replace A using this and put it inside and do the cubic, and we can get the answer of this. And then we want to calculate the density. So first we use N, which is how many atoms inside this unit cell, times the atomic weight of the element and divided by the volume and also the Avogadro number. Okay, so we put all the things that we know inside. 2 is here, and A is given here, and also the density is here. And this we know that is 6.022 times 10 to the power of 23. And then we can get the answer of R. So R will be equal to 1.43 times 10 to the power of minus 8 centimeter. And then we can change it into nanometer for us to eliminate this term. And you can stay like this, it will be okay. As for question 3.9, want to determine what kind of structure is these three alloys. Okay, so for this kind of problems, we can the only way we can do is just test by different kind of scenarios, such as simple cubic, body center cubic, or face center cubic. Okay, we just put inside and to test whether it is right or wrong. Okay, so for LOEA, we know the equation for density is like this, and this is the term that we need to test. We need to test it using BCC, A equals to this, or simple cubic, A equals to 2R, or FCC, A equals to 2 square root 2R. Okay, these are the things we need to test, and finally we can assume it is BCC and put this equation inside. And R we already know it looks like this, and we need to convert the unit. Okay, and finally we can get this is convert in the unit into centimeter, and then we put all the informations inside. Okay, and because BCC, so it's 2, and we know the atomic weight, and finally we can calculate the density is 6.4, which is matched, so this is a BCC structure. Okay, so for alloy B, we do the same thing. We assume it as a simple cubic, A equals to 2R, and N equals to 1. And then we put it inside to get the final answer of 12.3, and it is confirmed here, so we know that for alloy B, it's a simple cubic structure. And for alloy C, also we can do the same thing. And finally, we assume it as BCC, N equals to 2, and the equation A equals to this thing, and we put the atomic radius inside, and 2, and the atomic weight, and finally we can get the density equals to 9.6, which is fits in the density here. So we know the final structure of alloy C is also BCC. Okay, so this is how you do this kind of problem. And then for question 3.11, we want to know cobalt has an HCP crystal structure and an atomic radius of 0.1253 nanometer. And we also know the Ca ratio because we want to know the height of the HCP. So C equals to 1.6238. Okay, so compute the volume of the unit cell of cobalt. Okay, so for HCP, A equals to 2R. And then we want to calculate the volume of the unit cell, which is the base times the height. Okay, just like we mentioned before, C equals to 1.623 times A, and A also equals to 2R, so we can replace it using R to symbolize the whole equation. Okay, so we put the numbers inside, and especially the R, we can put it in here. And after the calculation, we can know that the answer equals to 6.64 times 10 to the power of minus 2 nanometers squared. Okay, so this is the volume of the unit cell. Okay, as for the next question, there's a few questions down here. So first, which crystal system does this unit cell belong? So we can check the angle and the length of this unit cell. We can see A, which A equals to B, but doesn't equals to C. So we can confirm the length is A equals to B and doesn't equals to C. And then we can check the angle. 3 of the angles are all 90 degrees Celsius. Not 90 degrees Celsius, 90 degree. And then we can confirm that this crystal structure is a tetragonal crystal structure. And how do we know this crystal structure be called? Here is an additional atom inside the middle of the base of this unit cell. So we can know that this is a body-centered tetragonal. And finally, we want to calculate the density of the material, given the atomic weight is 141 gram per mole. Okay, so we know the equation for the density, so we put this inside. For BCC, there's 2 atoms inside a unit cell, and here's the atomic weight divided by the volume of your unit cell, which is we can times these 3 things together to get this term. And finally is the Avogadro number. And then we can get the density of this material, which is 8.49 grams per cubic meter. Cubic centimeter. Sorry. Okay, so for 3.14, we want to sketch the tetragonal unit cell and indicate some locations. Okay, so normally the test won't ask you to determine the location. We will give you the location to ask you to determine what is its position. Okay, so it will be a bit easier than this because it is pretty hard to draw a 3D structure in a 2D paper. Okay, so for the first one, 1, 1.5, 1.5, we'll first go with the x-axis with 1, and then go with the y-axis with 1 divided by 2, and then go up with also a half. So it will be here. Okay, and then for the next one, we want to go half here, and then go 1/4 here, and then go up half here to get the final position. Okay, so this is a bit hard to draw, but it'll be okay on your test. For 3.16, we want to indicate the 2 directions, 2 vectors inside this cell. Okay, so for direction, I think the easiest way is just to use the endpoint to minus the initial point and also do the normalization. Like if it's x-axis, then you divide it by A, y-axis, then you divide it by B, z-axis, you divide it by C. So do the normalization, then you can get the answer. Okay, so for the 2 directions here, first direction is here, and the second is here. They both start from the original point. So the initial point will all be 0, 0, 0. Okay, so first you can take the final point for the direction 1, which is here. It is A minus 2 and minus half of B, and then minus C. So if you normalize by A, B, C, which means that you eliminate these terms, and then you can get 1, minus 1.5, and minus 1. And remember, if you want to symbolize it with a Miller index, you need to put the minus sign on the top, and also it needs to be an integer. So we need to times 2 to make it eliminate the 1.5 to become an integer. So the final answer will be 2 minus 1 minus 2. Okay. So for direction 2, we also want to know where's the end point. So it will be here. So it will be 2.5A, 0, and C. Okay, so we also do the normalization, and we can get 2.5, 0, 1. And then we want to make it into an integer form, so we times 2 to get the final answer 102. Okay, so for 3.17, we want to determine the directions by sketching it out. So I'll do it in a couple ways. You can decide which one you want to use. Okay, for 211 direction, we know in the x-axis we need 2, for y-axis we need 1, and for z-axis we need 1. So the direction like this. And for question B, 3 minus 1, 3, we can first do a couple of changes to make it more simple to draw it in a smaller scale. So for me, I'll change it into a more simple way by dividing by 3. You can divide anything you want, or you want to multiply by different things. You can do it either way. But for me, I'll make it into a smaller scale, so I'll change it by divided by 3. So it is 1 minus 1 divided by 3 and 1. So if we want to put it inside, then we know for x-axis we need a, for y-axis we need a b, and for c-axis we need a c. So it's a minus b divided by 3 and then c. So it's here. Okay, so for question C, we also want to do the same thing. I'll first divide by 2 to make something more simple. And so we put ABC back inside, so we know it's minus a, b divided by 2, and c. So it'll be like this. Okay. For the last one, I'll do also the same thing, divided by 3 to make something as 1. So it's a, 0, and c divided by 3. Okay, so there's nothing happening on the b-axis, so we know it's just a and c divided by 3. So the direction is here. Okay, that's all for 3.17. Okay, for question 3.22, we also want to know the index of the direction inside a hexagonal unit cell. Okay, so for hexagonal, it will be a little complicated, so I'll use 2 terms to explain both an easier way and a more complex way. Okay, so for the easier way, we can know that the direction is here, so we know in the planner there's a direction like this, added by a direction like that, and then we know for A1 and A2, it will both be minus A to get this direction. Okay, and for Z, it will be C. Okay, so if we normalize by A and C, you can know there's minus 1, and 1. So this is the direction. And for B, we will use a more complex way, but this will make you know the whole concept of how it works in hexagonal system. So we can take A1 equals to A, and A2 equals to half of A. So we can get this direction. The sum of this and that will equals to this. Okay, so we know there's no C, right? Because it's just here, 0. Okay, so we put n in all the three terms, and then we take a minus 0a because it starts from the origin. Okay, a minus 0a divided by a. This is the normalization that we'll do. And also the same for v is a divided by 2 minus 0a because start from the origin divided by a. So we can get 1.5. And then for w, it's just 0 because there's nothing happening on the z-axis. So we can get the answer of 1, 1.5, 0. And because in the middle index, we need to make everything into an integer form. So we need 2 times 2 to make the answer 210. Okay. For 3.25, we also want to sketch the planes inside a cubic system. Okay, so for you to do the sketching, I think one thing is important is that if we want to know what's the middle index of a plane, we first need to know the intersect of x, y, z, and then we do the reciprocal 导数, and then we turn it into a integer 整数. Okay, so if we want to draw the plane, we also do the same thing, but in a backward type. Okay, so first we know the middle plane is 1, 0, minus 1. So we do it back to the reciprocal, and then we know it's 1, infinity, minus 1. Okay, so this is the intersect for x, y, and z. So for x, it's 1. For z, it's minus 1. And for y, there's no intercept because it's infinity. Okay, so the plan will look like this. Okay, for b, 0, 1, 2, we can do the reciprocal and know it's infinity, 1, 1.5. Okay, so it's the intercept for x, y, z. So there's no intercept for x-axis, and the intercept will be 1 for the y-axis, and z will be in the 1.5. So it is this plane. Okay, for question C, middle plane is -1, 1, -1. So we also do the reciprocal and get -1, 1, -1. So these are the intersects. So -1 for x-axis and 1 for the y-axis, -1 for the z-axis. So we can get this plane. Okay, finally, it's question D, 3 minus 1, 2. We can also do the reciprocal to make it 1 divided by 3 and -1 and 1.5. Okay, so here is the point for x-axis, and here's the point for y-axis, and here's for z-axis. So we place it together and become the plane. Okay, this is how you draw a plane if you know the middle index. And then for 3.26, we do it in the opposite way. We want to know what's the middle index of the plane that it's given. Okay, so for plan A, it's a bit difficult because there's no intersect for the x-axis. So we need to find a new origin, which we find it here because we can know that there's 3 intersects in 3 directions. So it's definitely a place that we can place our origin. Okay, so for xyz, the intersects will be -1, -1, and 1. And we do the reciprocal to make it -1, -1, 1. So finally, the answer will be like this. And for plan B, we know that for the intersects of xy will be 1.5 and 1 divided by 3. And then for z-axis, there's no intersect because it is parallel to x-axis. So the reciprocal will be 2, 3, and 0. So the integer will be 2, 3, 0. Okay, so this is the middle index of a plane. Okay, so for 3.28, sketch the atomic packing of 111 plane for BCC crystal structure. Okay, so for 111 plane, we know the intercept will be 1, 1, 1. And this is the plane. So if we check it, we can check that the atomic arrangement will be like this, like 1 in the middle of 1, and the next will also be in the middle of these 2. Okay, so the atomic packing array will be like this. And for 3.31, we want to convert 0, -1, 2 plane into a 4-index Miller-Bravais scheme of hexagonal unit cell. Okay, so we know the 4-index term will be HKIL. So I equals to minus H added by K. So we know H and we also know K. So we put it inside and I will be 1. So we put I back into this term. So we can get 0, -1, 1, 2. Okay, pretty simple. And they're just, if you want to get the 4-index Miller-Bravais scheme, it is only just for hexagonal unit cell. It won't show up in crystal. It won't show up in cubic structure. Okay, for 3.32, want to determine the index for planes for the hexagonal unit cell. So first we want to know the intersects. So for A1 and A2, A1 will be infinity because it's parallel to A1. And then A2 will be -1. Okay. And then Z will also be infinity because it's also parallel to Z. So we do the reciprocal. So this 0 and this is minus 1 divided by a, and this is also 0. So we normalize using times a, so we can get 0 minus 1, 0. And if we want to get the 4 meter index, yes, if we want to get the 4 meter index, we also need to know I. So I put I back inside. Okay, so we do the same thing to question B. So A equals by A divided by, A1 equals to A divided by 2, and A2 equals to minus A, and Z equals to infinity because it's parallel to Z axis. Okay, and we do the reciprocal to get 2 divided by A and minus 1 divided by A, and then 0. So we normalize it times A and times C, so we can get the answer of 2 minus 1, 0. And we put I back into the term and can get 2 minus 1 minus 1, 0. Okay, for 3.37, we want to compute the inner planar spacing for 111 plane and 211 plane. Okay. So the material is an alpha iron, which is ferrite. So it's a BCC structure, and also know BCC structure A equals to this. Okay, and we can check the table to get the atomic radius, which is 0.1241. We place it inside to know how big is the A. The A equals to 0.2866 nanometer. So if we want to know the interplanar spacing or distance, we can use A divided by the square root of your numbers placing inside with a square. Okay, so we put 1, 1, 1 inside with a square. Okay, so final answer will be 0.2866 divided by the square root of 3. Okay, so we can get the answer of 0.1655 nanometer. And if you want to do it in the plane of 211, you can do the same thing. Put 211 inside the equation, and then we can get the answer of 0.117 nanometer. Okay, I think this is the last question. For question 3.38, we also want to determine something related to the diffraction angle. Sorry, this is 2 theta. Okay, so we know some information, which is the first order of reflection. So in here we know it's n equals to 1, and then we know it's a monochromatic radiation, so the wavelength is given also here, 0.19737 nanometers. And we know the crystal structure is of FCC nickel. So for FCC, A equals to this, and we can change it to the term of 2 square root of 2 times R, and R for nickel, FCC nickel is here 0.1246, so we can put it inside to determine A. And afterwards, we know how much is A. We can use the equation to get the interplanar distance. So we put A inside and get D equals, D for 111 plane is 0.2035 nanometer. And then we can put it back to the Bragg's law. 1 times 0.1937 equals to 2, which is here 2D. D equals to here, and sine theta. Okay, so you can use arcsine to get your theta equals to 28.46 degree. And the diffraction angle will equals to 2 theta. This is fixed. Diffraction angle always equals to 2 theta. So 2 times 28.42 equals to 56.84. Okay, so this is the final answer. Okay, so that's all for chapter 3's homework, and you can check it on your free time.